Let's look at intermolecular forces. To do that, I'm going to draw von Clobrecht, and these are actually von Clobrecht. That's how you can remember. See the size difference? It's showing electronegativity difference. So you're starting with the 4 dBi and towards 1 dBi of hydrogen, right? And then also you can think these will have a partial charge of delta negative for the von, but carbons and hydrogens will have a delta plus when it is covalently bonded to another nonmetal. So that's the nature of those, right? If we compare Cl is bonded to Br, that means chlorine is going to get delta negative, bromine is going to get delta positive, because it's a battle between the two components of the covalent bond. So the more electronegative one pulls the more electron towards it. Now, if you think oxygen and nitrogen bonded, oxygen will get the delta negative and nitrogen will get delta positive. So it's a comparison. Now look at this trend. So electronegativity trend, like I mentioned, it's like a wedge in this case, but you also can use the numbers. Starting 4 to 1, it goes like 4, 3.5 and so on. So you don't need to memorize it. I would say write the von Clobrecht and draw this wedge shape. So it's a electronegativity sort of qualitative ranking, right? So you have that one. Now, if the fluorine has a covalent bonded to hydrogen, oxygen covalently bonded to hydrogen, nitrogen covalently bonded to hydrogen, then only they can make the hydrogen bonding. Okay, that's the difference. Now, there are two differences here and you need to notice. Okay, so the hydrogen bonding is only for the von, F-O-N, but then any other pair within this this series, any other pair, something like fluorine to chlorine, hydrogen to fluorine, hydrogen to Cl, any other pair, different pair would have a dipole-dipole interaction, right? So this one, something like H to the Cl, it's not a von, right? C to the O, it's not a von, right? So they will have a sulfur to carbon, right? They will have a partial charge separation, delta plus delta minus, and something like F to the O even, right? Fluorine will get delta negative in that case, oxygen will get delta positive. So these ones are called the dipole-dipole. In the short version, you can say dip-dip. And that's the second category of intermolecular forces, right? The third category is, again, across everything, but any of the same kind of atoms bonded together, any of the same pair in a way, right? Same kind of pairs. So let's see what they are, right? You can imagine what they are. So these would be non-polar. So the non-polar means they are actually stuff like F2, O2, N2, carbon to carbon, even carbon to hydrogen, we call it as non-polar. They also call this interaction is called the London dispersion.